Well, hello, this is Math 31, and we are just beginning Chapter 4. This course is an introduction to calculus, and in Chapter 4, we are looking at extreme values. But before we get into any of that stuff, we have some review and preview of previous things you've learned and extending some of those ideas a little bit. So in this lesson, what we are going to be doing is looking at solving inequalities. So as you look at this first page in your notes, there are three warm-up questions here for you to do. The first two where you're solving these linear inequalities. Number two is a compound inequality, but I think you can figure it out. Number three, a quadratic inequality. You should have learned how to do this in grade 11, but take some time, work through these questions, see what you can remember. Once you have finished these three questions, then restart the video and you can see my solutions, and then we'll continue on with a few more examples. You can pause the video here. Well, here you see my solution for number one. We'll subtract the 6 on both sides of the inequality, multiply both sides by 3, and we get that x is greater than or equal to 24. And you'll remember with interval notation that we have this square bracket here to indicate we're including the 24, rounded bracket on the right side to say we're approaching infinity, but we remember that infinity is not actually a number, it's just an idea that we come closer and, well, can approach, I guess, put it that way. On to question number 2. Now, what you may have done in solving question number 2 here is you may have written two separate inequalities and then gone through the steps to solve each of them separately. But that's not what I'm going to do. Instead, what I'm going to do is I'm going to keep it as this compound inequality and then just make sure that whatever I do to one region, I do to all three of these regions of this inequality. So my goal is to isolate the x. So to get rid of this 1 that's being added to the negative 2x here, I need to subtract 1 in this middle section. If I do that in the middle section, I have to subtract 1 from the negative 7, and I need to subtract 1 from the positive 11. So that gives me this compound inequality that I now have in blue. Well, my next step, in order to get the x by itself, I need to divide this middle section by negative 2. But again, if I'm going to do that to the middle section, I need to do that to the negative 8 and also to the positive 10. So the negative 8 divided by negative 2 is 4. 10 divided by negative 2 is negative 5. But then we need to remember that if we divide by a negative, then the direction of the inequality switches. So the 10 divided by negative 2 is negative 5. We can see that this is smaller than the 4, which is on the left, which is a good indication that, oh yeah, these inequalities have to reverse signs, otherwise this original inequality won't have a solution. Now, when I rewrite this, I can switch it to put the smaller number on the left. Negative 5 is less than x, which is less than the larger number, which is a 4. Each of these signs is a less than sign, so I use rounded brackets in writing my solution in interval notation. Question number 3. Well, I hope you didn't square root both sides. As you learned in grade 11, if we have a quadratic inequality, what we need to do is to collect all the terms to one side of the inequality so that the other side will be a 0. And in this case, I factored the left-hand side and I thought of it as a difference of squares. Even though 11 isn't a perfect square, I treated it as though it were. And then when I do my difference of squares, I get x plus the square root of 11 times x minus the square root of 11. Now what we could do is we could say, well, this is giving me the zeros for my quadratic, and I know that I have a quadratic that opens up. So what you may have done last year is you might have looked at this and said, well, if I just look at my x-axis here, And I can say, well, there's 0, and there's negative root 11, and here's positive root 11. I know the zeros for this quadratic are here at the negative root 11 and here at the positive root 11. I did an open circle because I'm saying less than, not less than or equal to, so I don't want to include these 2 points. But then if I was to picture what does this graph look like, well, it's a parabola. I have a positive a value here, so it's a parabola that opens up. So I have this curve. Oh, that's not going to look good at all. Let's try that again. I have this curve. There we go. That's going to go up like this. And what I'm interested in is where is my graph less than 0? So where is it below the x-axis? Well, it's going to be below the x-axis for this entire region in between here. So this is how you may have thought this through last year, and we would say that the solution in this case will be from negative root 11 up to positive root 11. And again, we're not including the endpoints because it's less than but not equal to. Well, this is fine for a quadratic, and we know what the graph of a quadratic looks like. But we want to practice something where we don't need to depend on the graph because we're going to be looking at some more complex functions, higher degree polynomials, and also rational functions, and maybe even more complex than that. So here's another alternative for what we could do. Again, I can start with the zeros for my polynomial. But then what I'll do is I will select a test point in each interval. So here to the left of the negative root 11, I just picked negative 100. Why negative 100? Well, just because I know it's less than negative root 11. I could pick any number in this interval over here. So if I imagine that I have a negative 100, and if I was to plug that negative 100 in for this x, negative 100 plus root 11, well, I don't know what that's equal to, except I know that it'll be a negative number. So that's why I put a negative sign in this bracket here. This first factor will be negative if the x is a negative 100. And in fact, if it's any value here to the left of this negative root 11. Similarly, if I put a negative 100 in for this x, and I subtract negative root 11, I'll get a negative. So that's where this negative in the bracket comes from. Negative times negative gives me positive, so that tells me my function is positive in this entire interval. Is positive less than 0? No. So this interval is not something I want to include in my solution. Then I'll do another test point. Pick something in between these two zeros. Well, suppose I pick the value of 0. 0 plus root 11 is positive. 0 minus root 11 is negative. Positive times negative gives me a negative result. Is negative less than 0? Yes, it is. So I do want to include this middle section as part of my solution. Now, I think I'm going to have that drawn in a little bit later, but why don't I show it now already? And we'll say I don't want to include my zeros. And that's because this is less than but not equal to 0. But I do want to include this in-between interval because any number that I choose in here, if I plug it into these two factors, I get a positive times a negative, which gives me a negative result, which is why my graph goes down here. I'm getting negative y values. Now, keep in mind, I'm not thinking of the graph. I'm just thinking, is this function giving me positive or negative values? And I'm getting negatives in this middle interval. Then we'll look at this final interval on the right side, and we'll say, suppose I choose a number like 5. Why didn't I choose 100? Well, I could have. I just need anything bigger than the square root of 11. Well, the square root of 11 is a little bit bigger than 3, which is the square root of 9, and it's smaller than 4, the square root of 16, so I know 5 is going to be to the right of the square root of 11. If I plug 5 in here for x, 5 plus root 11, positive. 5 minus root 11, also positive, so I get a positive times a positive, gives me a positive, not a number less than 0, so I don't want to shade that interval. And so we have this solution with the interval shown there from negative root 11 to positive root 11. So this is the method that we're going to be practicing more and more because we don't need to know what the graph looks like in order to figure out the interval that will make this inequality true. So let's look at another example. Again, it's a quadratic. And as I mentioned in the previous question, we will start by collecting all the terms to one side and then factor it. At this point, I'm going to pause and let you finish this question. We know where the zeros are at x equaling positive 6 and negative 1. I would like you to do some test points in the 3 intervals that are created. So you can pause the video here, restart it once you've finished question 4. Well, here's my number line with a test point in each of the 3 intervals. Now, you probably didn't choose the same points as I did, and that's perfectly fine. Now, this time I have my quadratic is greater than or equal to 0. So since it can equal 0, then what's going on here? There we go. I do want to include the zeros of the 2 functions. So now I'm going to use solid dots instead of open circles. When I look at my test points, if I plug in a negative 10 minus 6 gives me a negative. Negative 10 plus 1 also gives me a negative. Negative times negative gives me a positive. So I know my function is positive in this interval, so this whole region over here will be part of my solution. And so as I sketch it on the number line, I'm going to include all of these points. Next, as I look when x is equal to 0, if I have 0 minus 6, that gives me a negative. 0 plus 1 gives me a positive. So notice I don't actually care what the value is because I just want to know for any point in this interval, will the result be positive or negative? Here, I'll get a negative because negative times positive gives me a negative. Is that greater than or equal to 0? No. So I don't want to include any points in that middle interval. And then we'll look at the positive 10. If I plug positive 10 in here, minus 6 gives me positive. 10 plus 1 gives me positive. Positive times positive gives me positive, which is greater than or equal to 0. And so I will include all of these points as part of my solution as well. So when I write this in interval notation, we will be going from negative infinity up to and including negative 1, and then from positive 6 to positive infinity, including this positive 6. Well, what if we go for a degree 3 polynomial? Well, don't groan too quickly. It turns out this one is factorable in a nice way where we don't have to use synthetic division to figure it out. We start the same. We collect all the terms to one side of the equation. And then notice, similar to when we do decomposition, because I have these 4 terms, I'm going to look and see, well, if I was to group my first 2 together and my next 2, can I pull out common factors? And it turns out that I can. So I can pull out a common factor of x squared from these first 2 terms and a negative 4 from the last 2 terms. Both of them leave me with the x plus 2 in the brackets, which is spectacular because now that green x plus 2 is a common factor that I can pull out to the front. That's multiplied to x squared minus 4, this x squared minus 4 left over, x squared minus 4, difference of squares. So now I have the factored form for this quadratic. And again, at this point, I will pause. Now we have 3 points on a number line, 3 zeros. Well, actually, it's kind of only 2 because one of them has a multiplicity of 2. I would like you to do some test points on the number line and then test each interval to see where we can find a solution to this inequality. So you can pause the video here once more, restart it once you have completed this question. Well, here you see the test points that I've chosen. And when I plug that value into each of the factors, if I plug a -10 in, this will give me a negative, a negative, a negative. 3 negatives multiplied together give me a negative. Is that greater than or equal to 0? It is not. So this is not part of my solution. This -2 here is part of my solution. So is the +2. So I'm going to put the dots there right away. And then I'll plug in 0. 0 plus 2 is positive. 0 plus 2 is positive. 0 minus 2 is negative. Positive times negative gives me a negative. So there's a good caution for us. Don't automatically assume that the intervals will alternate between positive and negative. In this case, we have 2 negatives and the 0 in between. And as we think about this, oh yeah, what I could have done earlier is I could have rewritten my factored form so it looked like this. So then I see that I have that multiplicity of 2, which means my graph is just barely touching the x-axis at -2, but then it's staying on the same side. So using what you learned in Math 30-1, we know at this point that our graph is going to be curving like this at this point. Well, let's do our last test point, +10. 10 plus 2, positive. 10 plus 2, positive. 10 minus 2, positive. Positive times positive gives me a positive. And so my solution will be this interesting looking interval. Now here using interval notation, I do have to include this point where x is -2. How do I include it in interval notation? I just say I'm going from -2 to -2, including both endpoints. So this is just describing that single point here where x is -2. And then also, since I had a positive here to the right of this 2, I'm also including all of these points there, and that's this 2 to infinity, including the 2, so we have the square bracket when we do interval notation. There you have question 5. Number 6. Well, when we're solving an inequality that has rational expressions, we still need to do it kind of like we did with the polynomials, where we collect all the terms to one side. So I'm going to subtract that 2 to the left, so my right-hand side will be equal to 0. But I need to do some simplifying here, collecting these two terms together. So I need a common factor of x minus 3. So I'll multiply the 2 times x minus 3 over x minus 3. Multiplying it by 1 doesn't change its value, it'll just change how it looks. Once we get that expanded, that will give me a -2 times x, which will be the -2x. This -2 times -3 is a +6. So be careful with that sign. That will be a +6 at the end. And then when we combine the x's together in the numerator, here's what we'll get. 6 minus x on the top and x minus 3 in the denominator. Now with a polynomial function, we started by factoring and finding the zeros of the polynomial, and we used those to divide up our number line into intervals. We need to do the same thing here with this rational inequality, but we also need to consider the non-permissible values. With rational inequalities, we must consider test points on intervals determined by both the zeros and also by the non-permissible values. So as we look at the inequality that we have here, we can say we have a 0 where x is equal to 6. That makes the numerator equal to 0. And we have a non-permissible value where x is equal to 3. So we have these 2 points that will be important for us to consider on our number line when we divide it into intervals. So here we go. I have the 3 and the 6 on my number line. And now I'll do some test points at 0, 5, and 10. Plug in the 0. 6 minus 0 is positive. 0 minus 3 is negative. A positive divided by a negative gives me a negative. Is that greater than or equal to 0? No. I look at my next point. 5. 6 minus 5 will still be positive. 5 minus 3 will also be positive. So here I will be positive in this interval. And then let's plug in the 10. 6 minus 10 will be a negative. 10 minus 3 will be a positive. Negative divided by positive gives me negative. So I'm negative in this interval. So my function is not defined where x is 3, so that cannot be part of my solution. I need an open circle. I have a 0 where x equals 6. 6 minus 6 is 0. That is greater than or equal to 0. So I do want to include this point in my solution. And then I want positive values, which means I will choose all the values in this middle section here. And so my solution will be from 3, oops, I did the wrong bracket there. Be careful, Mr. Wagner, or I'll have to give away candy, not including the 3, but I am including the 6, and there is my solution. Well, why stop there? One more example before I give you some check your understanding questions to try. Here we have a more complex rational equation, or inequality, I should say. The right-hand side is already 0, which is kind of nice. It'll save us some work. But I need to look at where are the zeros in this rational expression and where are the non-permissible values. So let's look at that denominator in factored form. This x squared minus 4 is an x plus 2 times an x minus 2. But they're both being squared because I have x squared minus 4 all squared. So I just squared each factor separately. Now that I have this in factored form, I would like you to set up the number line with the test points and see what you get for a solution. So again, I'll ask you to pause the video at this point and restart once you've finished question number 7. Well, here you see my full solution. How does it compare to yours? Well, let me go through the steps again with you. I have my non-permissible value at -2, at +2, and I have a 0 where x is +1. So that's where those 3 values came from. Dividing up my number line into 4 intervals, I pick a test point in each interval, the 10, the 0, the 1.5, and the +10. I guess this was a -10. Then I see what's going to happen. Well, I know no matter what I do, since this factor is squared, this will always be positive. This will also always be positive because it's squared. So I don't have to work through every single point. I can be a little bit smart here and say my denominator is always positive, or 0, which will be where my function is undefined. So all I really need to look at is to the left and right of where x is -1. So I'm going to look at this -1 here, and I'll go to left, plug in the 0. 0 minus 1 is negative. Negative over positive, is that less than or equal to 0? Yep, that's going to give me negatives. And that's going to be true for this entire region here. It'll be negative. Now I could pick -10. Oh, -10 minus 1 is -11. But the denominator is always positive, so why do multiple points? It's unnecessary. Just to kind of give yourself a little bit more uh, confirmation, you can do more test points, but it's not necessary. Then if I pick a number to the right of x equaling 1, let's go with the 1.5. 1.5 minus 1 is positive. Positive over positive gives me positive for this entire interval to the right side here. So in this case, the non-permissible values were kind of useless for the test points. But I need to keep in mind that since this expression is not defined when x is -2 and when x is +2, -2 and +2 cannot be included in my solution. So even though my test point said I'm negative everywhere here to the left of x equaling 1, I have to remember to exclude where x is -2. And so here we have my solution. Well, hopefully that's enough to get you started. Why don't you work through these two check your understanding questions, and then that'll be it for this lesson. So you can pause the video now, restart it once you're ready to check the answers. Here's my solution for number 8. The numerator can be factored, the denominator cannot. So I look to see where is this equal to 0. Denominator can never equal 0. So there are no non-permissible values for this inequality. I only end up looking at the zeros of the function. Now I put a 0 in here just in between the -2 and +2 and use that as one of my test points. And then here you can see that I've shown down here, if I plug in the -10, -2 is negative. That's where this negative comes from. -10 minus 2 or +2 is negative. -2 also negative, so they're both negative factors in the numerator. Since I'm squaring whatever my x value is and adding 1, my denominator is always positive. So here we have the 3 test points. I get my solutions in this middle interval and rounded brackets saying that my x can be between -2 and +2, not including the endpoints. Question number 9. The numerator is already factored. The denominator I could factor further, and you'll notice I factored that quadratic and then kept it inside a bracket all being squared. Well, that's different than what I did in question 7. In 7, I squared each factor separately, and we could have done that in 9 as well. Or the method we used in 9, we could have done in number 7. So it doesn't always have to be the same way. I wanted you to see the variety here, how we could write it differently. And the fact that this is squared is useful because it tells me my denominator is always positive except when it's 0. So here we have an interesting situation. Because we have this common factor, which gives me a point of discontinuity, well, it looks like it. But because this factor is squared, it turns out not to be a point of discontinuity. So I need to consider, when x is -4, -2, +1, and the intervals created by those points. So as I come across here, I'm looking to see where is it equal to 0? Well, it's equal to 0 at those points. But I think I don't want to write the points all like that because -4 is non-permissible. So instead of using that, I'm going to say I have a non-permissible value here where x is -4 and my function is equal to 0 when x is -2 and where it is equal to -1 or +1. Then I can see what's going to happen. Well, again, because this factor that's squared and this whole denominator that's squared, those are always positive. So this is positive, this whole thing, always positive when it's not 0. Really all I need to look at is on either side of x equaling 1. So here's I look at either side of x equaling 1, I get a negative for each of these test points. I could have picked any one, and I get positive when I plug in the test point to the right side of the 1. And now as you look at my solution here, you'll say, oh, there's a mistake there, isn't there? Yeah, there is a mistake. This should not be included. Why did I put a 5 there? Yeah. So we'll just pretend we didn't even see that. I'll have to fix this for the future. But where is it greater than or equal to 0? Equal to 0 here at -2. So again, from -2 to -2 inclusive. And then from -1 up to infinity, including, I should say the +1 up to infinity, including the +1. Oh, well, a little bit of misspoken uh, answers here, confusing my positives and negatives. So this is a good place to stop this lesson because my brain is not in shape after this 2 weeks of spring break. But there you go. Review and preview. How do we solve inequalities? So you have some practice to do in your textbook, 2 pages. On page 163, I think it is, and also on page 166. So you have the rest of this class time to work through those practice questions. Alrighty, take care.